All right, so you guys are gonna get, you're gonna work with a partner. I will pick your partner, so don't get all excited. You're gonna get 2 pieces of paper. The first side is gonna have 6 descriptions of motion. The back is gonna have 6 different, it's the same paper, but one you're gonna have like 1 through 6 up. On the other side, you're gonna have 7 through 12 up, because you wanna see all 12 situations at once. All right, so you're each gonna get a piece of paper, but one of you will have it 1 through 6 up, one of you will have it 7 through 12 up. You're also gonna get a baggie, and in the baggie are 12 little diagrams, okay? The diagrams have like the little square for the item that is moving, and then it has arrows with our force app, force grav, force norm, force air, all of those types of forces that we've been talking about, okay? And so what you're gonna do is you're going to end up matching one of the cards to the description. And so the free body diagram, the card that you're gonna put, with this description is obviously gonna have to be the free body diagram that you're saying matches this description, okay? And so you're not drawing or writing on the pieces of paper that I give you, and because if you get them wrong, I'm gonna come around, and if you're getting them wrong, then I just move them off and be like, check that one, check that one, check that one. It's not like you have to erase everything, and it's not something that you're gonna keep, okay? So the cards are just going to sit on the piece of paper. So if you think that, this little card with this free body diagram matches this situation, this card would just lay right on the paper, okay? So here's the trickier part of this. And I'll put some hints on the board, some things that will help. But it says it all right here. This one actually says you're gonna draw them because this is one that like we've done before, like as an assignment. But you're gonna make sure, the important thing is that you look at the arrow length, all right? Because the arrow length is gonna tell you whether or not you are having something that is like on cruise control, where it's constant motion, or whether it's accelerating. If it's accelerating, you're gonna see a longer arrow. If it's just at constant motion, you're gonna have an arrow that is equal to the opposite direction. So, you'd have something that looks more like this. Right, so if you have an arrow like this, and an arrow like this, they're equal in length, pretty close, and so they're gonna be constant. If you have arrows like this, are those equal in length? No, so this one's gonna be showing an acceleration, all right, and I'll put up a few more hints as you're working. But I am gonna also give you another paper that has all these hints on them. All right, so here's the thing. The situation, the little description, has to say a force was applied for you to choose one of your little 12 drawings that has force app on it. Because if the force is applied, it physically has to be being applied at that moment. So if I have this book, I'm applying the force to it the whole time my hand is actually in contact with it, right? If I apply a force and then I look at the object's motion and my hand is not attached to it, like I'm not actively pushing it, then that is not an applied force. We know that an applied force had to have taken place to get that book moving. So if I give this a tap, I know that I applied a force to get it to move, but let's say halfway through its motion, I take a picture of it, all right? So I take a picture. If I take a picture when my hand is not touching it, I know if that object is really in motion, that I had to have applied a force to get it to move at some point. And so that's the thing that's hard. People are like, it couldn't have been moving if there was no force applied, so I have to have a force applied. But it's only going to have force app in the diagram if the object is actually having that force applied. Because remember, an applied force is a contact. If the contact is no longer there, then we know that to get it going, there had to have been an applied force. But at the moment of the little description or the diagram, at the moment that this was drawn to describe the motion, that hand or that foot was not attached to the item, actually physically causing it to get moving. all right? And so that tends to be the hardest part. And I'll show you a couple examples, but that's one thing. It also has to say force of fric, which is friction, is always going to work opposite motion. So if it says it's accelerating to the right, motion's to the right, that means friction would be working left. All right, so keep that in mind. Obviously, gravity is always going to be pulling downward. So unless it says ignore gravity or something like that, you have to make sure that, you know, it has that force of gravity in the description. The only time normal force can be in this little diagram is if it is a solid to a solid. So if something is in free fall, is that object going to be a solid to a solid? Well, you're going to have to think more than that today. No. Correct, no, right? Because if my book is falling, it's a solid, but it's not touching another solid until it reaches my tabletop. This would be an object that has normal force. As it's falling, it would be an object that does not have normal force. So you have to ask yourself, is it in free fall? If it is in the air, then it's going to have force of air, which is air resistance. So as this book is falling, it's experiencing air resistance, right? But some of these examples will say ignore air resistance, just because. So obviously we know that it's working, air resistance is acting on it, but for that specific example, it wants you to ignore it. So you cannot pick one of these that has force of air if it says ignore air resistance. Here's what I just drew up on the board. If the speed is constant, then the arrows are going to be equal in length because the forces are balanced. If the speed is changing or accelerating, then you're going to have arrows of unequal length. Okay, so back to some of your descriptions here. So it says a rightward force is applied. If it says force is applied, then like I am actively touching it and pushing it or pulling it. So that would have to have a force applied as one of the forces on the little diagram. Constant speed is going to stick out to me, and I'd be thinking, okay, which one is constant? Well, constant is going to be where the arrows are equal. So you're going to have arrows of equal length, but in opposite directions. Okay, and then it says ignore air resistance. Right, so you're going to have to find the diagram, the little card that has a diagram that best matches that description. Right, I think the easiest thing to do is have, you know, one of the papers 1 through 6 up, one of the papers 7 through 12 up, and then in the middle have all 12 of your cards face up. And then that way you guys can kind of talk through, you can see all of your options at once. Okay? Probably the hardest part is the idea that people want to put normal force for everything, and you can't have it if something is like in free fall because it's not a solid to a solid. And the other one is that they want to put an applied force because all of these things are moving, whether it's constant like cruise control or whether it's accelerating, and those are unbalanced forces. But only a few of them actually say a force is applied, a force is applied. So like this one, it says a football is moving upward and rightward towards the peak of its trajectory, which is the highest point. It doesn't have a force applied. People always want to put an applied force for this diagram, but it doesn't say a force is applied to the football. Now, I understand that a person's foot had to have made contact with that football to get moving, but because it doesn't say that, you can't use the diagram that has a force app in it. The other one, sometimes that people forget about is our force of tens, which is tension. There's going to be a couple that have the force of tension, and so it's like a hanging force. So like a rope hanging from a limb for like a tire swing, or maybe even like a regular swing set where the chains are attached to the crossbar. That's going to be dealing with a hanging force. Gravity's pulling down, that tension is pushing up. Okay, so you know, if something is hanging or suspended, you're dealing with that tension, that pulling force. Okay, any questions? One paper 1 through 6 up, one paper 7 through 12 side up. Put all the cards face up in the middle and make sure that you can see all of them to help you as you get going. You can, when you start to get them and